Hello everyone, I hope you all are fine. Today we are going to do the chapter of Inorganic Chemistry of BSc, that is Chemistry of Noble Gases. The elements helium, neon, argon, krypton, xenon, radon comprise noble gases. The group of noble gases is regarded as zero group or group 18 of the periodic table. These are gases at ordinary temperature and do not have chemical reactivity. Due to chemical inertness, these were called inert gases. However, nowadays a number of compounds of these gases, particularly of xenon and krypton, have been prepared. This shows that these gases are not completely inert. Consequently, these gases are now called noble gases instead of inert gases, which signifies that these gases have some reactivity. Because of low abundance of these gases on Earth, they have also been called rare gases. The atomic numbers of these gases are 2, 10, 18, 36, 54, 86. The way to remember the atomic numbers, I have told you in the previous video. You will get the link of that video in the description box. In this way, you can learn all the atomic numbers. And the general electronic configuration of these gases is Ns2Np6. So you can see here that the electronic configuration is a full-filled stable configuration. So due to the stable electronic configuration, noble gases are monoatomic and they are colorless and odorless because they are fully filled. In noble gases, atomic radii corresponds to van der Waals radius, which increases down the group due to addition of new electronic shells. The first ionization energies are very high because you know that it has a stable, fully filled configuration. Due to stable Ns2Np6 configuration, noble gases atoms have no tendency to accept additional electrons. That means electron affinity of these atoms, of these elements, is zero. Noble gases have low melting point and boiling point because of no strong interatomic forces. That is, it has van der Waals forces which are weak forces, and these forces increases on increasing size of the atom. So down the group, size of atom increases. That means the forces between the atoms also increases. Ease of liquefaction increases down the group because of more van der Waals forces. So just keep in mind, more the van der Waals forces, stronger will be the bonding of these atoms. Slightly soluble in water. So these gases are slightly soluble in water, and the solubility increases from helium to radon. As I told you that the van der Waals forces between these increases, or we can say the extent of polarization also increases. That is the dipole induced dipole. Dipole means for polar, that is water, and induced dipole means noble gases. That means water will induce a dipole, will induce a charge into the noble gas, which is neutral. Now let's come to the main topic of this chapter, that is compounds of xenon. The question will come from this section mostly. Xenon in +2 oxidation state, xenon in +4 oxidation state, xenon in +6 and +8 oxidation states. We have 4 oxidation states in which xenon exists. So let's have a look over the first, that is +2 oxidation state of xenon. The compound which is in +2 oxidation state of xenon is XeF2, that is xenon difluoride. How do we prepare? Xenon plus fluorine. When fluorine reacts with xenon, it forms xenon difluoride. So what are the conditions? The conditions are, there can be 4 conditions. We can do this in 4 different conditions. The first condition is 400 degrees Celsius temperature and in the presence of nickel, right? So you can do this, the reaction with this condition, or the second condition is you can use electric discharge, or we can use mercury vapors, or the fourth reaction, that is xenon plus O2F2 gives XeF2 plus O2 at a temperature of minus 78 degrees Celsius. Let's see the physical properties. It is a colorless crystalline solid. Its melting point is 129 degrees Celsius. It is least volatile of xenon fluorides. Stable in pure and dry state and can be obtained in nickel containers. Can be contained. And it dissolves in HF. Xenon fluoride plus hydrogen gives xenon plus 2 molecules of HF. It gives substitution reaction with strong protonic acids. XeF2 plus HX gives FXeX plus HF. FXeX plus HX gives XeX2 plus HF. So you can't understand the reactions just by listening. You have to write it along with me and try to understand from where the element is being displaced, from where the element is being substituted, because these are substitution reactions. In this reaction you can see that one fluorine leaves, and in place of fluorine X joins. X is a group. It can be ClO4 negative, CF3CO negative, SO3F negative. So this group joins in place of one fluorine. So we get FXeX now. And from here we get HF, right? Similarly, in the other reaction, from here fluorine goes and this X group joins. We get XeX2 plus HF. It slowly but completely hydrolyze in acidic or neutral medium or alkaline medium, right? So XeF2 plus water gives Xe plus HF plus O2. So it is getting hydrolyzed. XeF2 plus NaOH, that is an alkaline medium also. Let's see. It gives Xe plus NaF plus O2 plus water. It oxidizes iodine in the presence of BF3 to give IF. In all these reactions you can see we get IF here. XeF2 plus I2 in the presence of BF3 we get IF. That means iodine plus fluorine gives IF and xenon as it is. So next we have XeF2 plus NO gives NOF plus Xe. These reactions are just to show the reactivity of xenon difluoride. So here we say that it reacts with NO, NO2 and SO3 as well. So these are just to show the reactivity of XeF2. It is a mild fluorinating agent. XeF2 is a mild fluorinating agent. Thus, it reacts with benzene to give fluorobenzene. What is benzene? Benzene is C6H6. If we remove one hydrogen and write fluorine in place of it, so we get fluorobenzene. So, it is a fluorinating agent. It also fluorinates ethylene to 1,1-difluoroethane. This is ethene and this is xenon difluoride. When they both react, we get 1,1,2-difluoroethane. Right? Let me correct it here. It must be 1,2. Alright. So it also acts as oxidizing agent. Just note these points. These are the main points. Like it is a fluorinating agent. It is an oxidizing agent. Then in the exam, the examiner will ask you to explain and to give examples of this. So you have to just write the examples to write that it is a fluorinating agent, it is an oxidizing agent. So being a strong oxidizing agent, it oxidizes HCl to chlorine, cerium in +3 state to +4 state, chromium in +3 to +6 state, BrO3 negative to BrO4 negative. So you can see that the oxidation states are increasing in positive way. So these are getting oxidized. In this reaction you can see BrO3 negative plus XeF2 plus water gives xenon. So here, okay, let me tell you how the oxidation states are changing. Let the oxidation state of bromine be X, and from oxygen it will be -2 into 3 will be -6 is equal to -1. So which implies X is +5 in this case. And in here we have X minus 8 is equal to -1, which implies X is equal to +7. So the state of bromine is changing from +5 to +7. That means it is being oxidized. BrO3 negative is being oxidized, and the oxidizing agent is XeF2. Alright. Now, xenon difluoride in anhydrous HF, that is hydrogen fluoride, it reacts readily with platinum metals or sulfur powder or iridium to produce highest fluorides. As you can see, PtF6, SF6, iridium F5. So these are highest fluorides which are produced on reaction with HF. Alright. In BrF2 solution, xenon difluoride act as a Lewis base and form adducts, right? It acts as a Lewis base and it forms adducts with compositions XeF2, MF5, XeF2.MF5, right? So let's see. This is XeF2 plus SbF5. Now this acts as a Lewis base. Lewis base donates lone pair of electrons, right? So it forms an adduct. Alright. These compounds exist as ionic species like XeF plus, FB, SB, F6 negative, and XeF positive, AsF6 negative. XeF2 when reacts with SbF5, it forms XeF2.2SbF5. The compound XeF2.2SbF5, this compound has been shown to contain XeF positive and Sb2F11 negative ions. The XeF positive ion is strongly bonded to Sb2F11 negative by a fluoride bridge between xenon and antimony. The ion contains two octahedral linking between the shared F fluorines. So this is the octahedral linkage, one you can see in the figure. XeF2 also reacts with the arsenic pentafluoride in a different stoichiometry, like XeF2 two molecules plus the arsenic fluoride pentafluoride, it gives XeF2.AsF5, 2 with this one. So it exists as ionic species also, Xe2F3 positive, AsF6 negative. Xe2F3 positive, it has a linear geometry around xenon and angular geometry around the xenon fluorine. So you can see in this figure that it has a linear geometry along xenon and angular geometry at fluorine, like this. Okay, so these were compounds of xenon in +2 oxidation state. So let's see the +4 oxidation state of xenon. It is xenon tetrafluoride. The first compound we are going to study in +4 state is xenon tetrafluoride. That means 4 fluorine. Xenon combines with 2 fluorine to form XeF4. They combine in a molar ratio of 1:5 in the presence of nickel at 400 degrees Celsius, 5 to 6 atmosphere pressure. Or you can use the second condition, that is electric discharge at minus 78 degrees Celsius in the molar ratio 1:2 at a pressure of 2 to 15 millimeter mercury. It is a colorless crystalline solid which have a melting point of 117.1 degrees Celsius, sublimes easily, right? It dissolves in IF7 and HF without reacting, and it is oxidized by hydrogen at 30 degrees Celsius. You can see that XeF4 plus hydrogen gives Xe plus 4HF. So if you are listening to me carefully, you must have noted that I have said oxidized by hydrogen at 30 degrees Celsius. It must be reduced. It should not be oxidized. How can hydrogen oxidize anything? So hydrogen XeF4 as xenon is in +4 oxidation state, and it is going to 0 oxidation state. So it is being reduced, and the hydrogen is converting from 0 to +1 oxidation state. That means the hydrogen is getting oxidized. Alright? It is a better fluorinating agent than xenon fluoride, difluoride. So mercury when reacts with XeF4 gives xenon plus HDF2. Platinum on reaction gives PtF4. SF4 on reaction with XeF4 gives SF6 plus xenon. It also reacts with BCl3 to form BF3. Let's see how. Xenon tetrafluoride on reaction with BCl3 forms BF3 plus xenon plus chlorine. That means the fluorine ions are transferred here and the chlorine forms Cl2. It forms BF3 and the xenon as it is. It undergoes disproportionation in water, giving a highly explosive solid compound, that is XeO3.6. Okay, let's see this. It is very interesting. This is XeF4. On addition of water, on reacting with water, it forms xenon plus XeO3 plus HF plus O2. This XeO3 is a solid compound and it is explosive, right? But if the reaction is controlled at minus 80 degrees Celsius, it forms xenon oxyfluoride. That is xenon tetrafluoride plus water at minus 80 degrees Celsius gives xenon oxyfluoride plus HF, right? It combines with molten TaF2 to form straw colored xenon compound, which is XeTaF6 whole twice. Alright, so this is a reaction. It forms an addition compound with SbF5. XeF4 plus SbF5 gives this compound. This is an addition compound. Just put a dot between both the compounds, or you can show that in form of ions also. That is, just remove one fluorine from here, you get XeF3 positive, and add one fluorine here, you get SbF6 negative. Is a correction. It's 5, right? So XeF4 plus 2 SbF5 gives XeF4 plus 2 SbF5 here also. So when one hydrogen fluorine is removed from here, it gets positive charge, and on addition of one fluorine here, it gets a negative charge. So the next compound is xenon oxyfluoride. It is prepared by slow and partial hydrolysis of XeF4, that is the compound we have just prepared in the previous reactions. It is xenon tetrafluoride. So by slow and partial hydrolysis of xenon tetrafluoride at low temperature, we can get xenon oxyfluoride. Alright, so it is not a very stable compound. The structures of all these compounds we are going to do at the end. Alright, So next we have xenon in +6 oxidation state. The first compound is xenon hexafluoride. Preparation: xenon plus fluorine gives XeF6 at 250 to 300 degrees Celsius and in the presence of nickel vessel, right, at 50 to 60 atmosphere pressure. So these conditions are important to perform the reaction. Next we have xenon tetrafluoride plus O2F2 at minus 130 degrees Celsius forms xenon hexafluoride plus oxygen. This is called oxidation of xenon tetrafluoride. As you can see that we are oxidizing it to xenon from +4 oxidation state to +6 oxidation state. So this is an oxidation, right, by passing electric discharge, as we have read in all other reactions also, right. Next we have XeF6 can be separated from XeF2 and XeF4 by passing through NaF, which absorbs xenon hexafluoride at 17 degrees Celsius, giving Na2XeF8. So we can separate XeF6. 2 molecules of NaF in the presence of this gives the compound to separate the xenon hexafluoride. On warming this at 120 degrees Celsius, pure xenon hexafluoride is evolved. So this is a way to separate xenon hexafluoride. Let's see the properties. It is a solid crystalline substance. It melts at 49.5 degrees Celsius. It is most volatile of all fluorides of xenon. Its vapors have a greenish yellow color. So these are the points through which you can remember which compound was performing which reactions. Just correlated with their colors and you will be able to remember the compounds. HF plus XeF6 forms XeF5 positive plus HF2 negative. So it is a good conductor because it is forming ions, right? It is reduced to xenon by hydrogen, ammonia, HCl, right? So it forms xenon plus HF, NH4F, chlorine, etc. It undergoes slow hydrolysis with atmospheric moisture and forms XeO3, which is highly explosive. This is also, we have already done one explosive compound reaction. Let's see this one. Here also XeO3 was formed, which was explosive. Now in this reaction also we get XeO3, which is explosive. So just remember, if explosive compound is being asked or the reaction is being asked, so just remember that they are talking about XeO3, right? And therefore we have to be carefully hydrolyze it in nickel vessel, right? So careful hydrolysis in nickel vessel give colorless stable liquid, which is XeOF4. XeF6 plus water gives XeOF4 plus 2HF. It is extremely reactive. Therefore, it cannot be stored in glass or quartz vessel because of the following reactions, which finally give the dangerous explosive xenon trioxide, this one, right? So let's see which reactions they are talking about. It is XeF6 on reaction with O2, silica, quartz, glass, right? So we get XeOF4 plus SiF4. Now this, okay, how to remember these reactions? In this reaction you can see that there are 6 fluorines. If we, okay, do you know what is the valency of fluorine and what is the valency of oxygen? Valency of fluorine is -1 and for oxygen it is -2, right? So if we do 2 times the valency of fluorine, we get the valency of oxygen. So if we remove 2 fluorines and add 1 oxygen, we get the same oxidation states of all. So here, if we have removed 2 fluorines, we get 4, and we have added 1 oxygen in place of those 2 fluorines. Just, this is a trick to remember, right? So we get SiF4. Now this compound, again we remove 2 fluorine, add 1 oxygen, Xe2F2, where then again we remove 2 fluorines and add 1 oxygen, we get XeO3, the compound which is explosive. Alright, it reacts with fluoride ion. It reacts with fluoride ion acceptors to form adducts. Right, so this is XeF6 plus PtF5, then it forms adducts or the ionic form of this, and the same reaction goes with antimony arsenic. Next we have XeF5 positive. This one has square pyramidal geometry. It has a square pyramidal geometry, you can see. With fluoride ion donors, it forms XeF7 negative and XeF8 2 negative species. Like cesium fluoride plus XeF6 gives cesium dot XeF6 adduct, or you can see this in ionic forms. Again, the reaction with the rubidium, and it also has a square anti-prismatic structure. The structures of all compounds, I have already told you that we are going to do that at the end. We have already done 4 compounds. This is the 5th compound, XeOF4 xenon oxytetrafluoride. By partial hydrolysis of xenon hexafluoride, we get XeOF4 plus HF. Then on reacting with SiO2, it gives that product XeOF4. As soon as the yellow color of XeF disappears, the contents are immediately quenched with solid carbon dioxide. It is done to avoid the formation of the explosive compound. You must remember this, XeO3, this is explosive, right? It is XeOF4 plus SiO2 gives XeO3 plus SiF4. Xenon in presence of large excess of oxygen plus fluorine at a temperature of 230 degrees Celsius gives XeOF4. So these are 3 types in which you can prepare xenon oxytetrafluoride. So it can be prepared by vacuum distillation in this reaction. Right. Next we have, it is a colorless compound. Melting point is minus 46 degrees Celsius. It do reduction on reaction with the hydrogen to form xenon. It reacts with water or silica to form another oxyfluoride, XeO2F2. So you can see that in XeO4 OF4 there are 4 fluorines here. So we remove 2 fluorine, add 1 oxygen, we get XeO2F2. In this, xenon remains in the same oxidation state, I have already told you. Further give explosive compounds. That means if we remove these 2 fluorines also to add 1 oxygen, we get the explosive compound. And similarly, on reaction with silica also the same reaction occurs. It reacts with fluoride ion acceptors to form XeOF3 positive cation. Right? On addition of excess XeOF4 plus SbF5, we get this XeOF3 positive plus SbF6 negative. XeOF4 reacts with nitrosyl fluoride NOF to give crystalline compound NO positive XeOF5 negative. So this is the reaction. The next compound is xenon trioxide. Let's see the preparation. XeF4 on addition of water gives XeO3 plus 4 Xe6HF and oxygen. And XeF6 plus 3 water gives again XeO3 explosive compound. We have already done this reaction. Remove 2 fluorine, add 1 oxygen. Remove 2 fluorine, add 1 oxygen, and finally we get the explosive compound here. So the next compound is xenon dioxydifluoride, XeO2F2. The preparation is on addition of XeOF4 into XeO3, this explosive compound. On addition of XeOF4 to this explosive compound, we at minus 78 degrees Celsius, we get this xenon difluoride. It can be purified by fractional distillation, right? Now on reaction with silica, it forms again xenon difluoride. Or reaction with water, again we get the product. Colorless solid, all were colorless till now, right? Melting point is 30.8 degrees Celsius. On reaction with water, it forms that explosive compound plus HF, thermodynamically unstable. XeO2F2, it gives XeF2 plus oxygen. That means it is an unstable compound. It reacts with SbF5 in HF and gives a white solid of composition XeO2F positive, SbF11 negative. It is Sb, antimony. Alright, this compound is unstable at room temperature and slowly decomposes to give XeF positive, Sb twice, F11 negative, and oxygen. The next compound is xenon trioxide. The preparation is XeF4 plus water gives XeO3 plus xenon plus HF plus oxygen. Then again on adding water to XeF6, we get the same product. We are talking about xenon trioxide. This is the explosive product. However, the last reaction proceeds through the following steps. Remove 2 fluorine, add 1 oxygen, and so on. Great care should be taken during its preparation because it is highly explosive. XeO3 is a white, non-volatile solid. So this is white in color and it is non-volatile, it is solid. It is soluble in water. It is quite stable in aqueous solution. However, it explodes violently when dry, right? It forms xenon plus oxygen and releases amount of energy, so it is highly explosive. Acts as a powerful oxidizing agent in acidic medium. When Pu3 positive reacts with XeO3 in the presence of hydrogen, that is acidic hydrogen, we get PuF4 positive. It is being oxidized, right? Oxidized. So what is the oxidizing agent? That is being reduced, that is getting reduced. Here xenon is going from plastic state to 0. That means it is getting reduced. So this is an oxidizing agent. So XeO3 is an oxidizing agent. It undergoes disproportionation when dissolved in NaOH and forms sodium perxenate. This is the compound, right? Sodium perxenate, when dissolved in an acidic solution, decompose slowly to give XeO3 and O2, as you can see here. So Na4XeO6 on addition of HCl gives NaCl plus H4XeO6. Now this further gives XeO3 plus water plus oxygen. So next we have xenon in +8 oxidation state. There are compounds like XeF8, XeO4, XeOF6, XeO3F2, XeO2F4. These can be prepared. This compound XeF4, it is successfully prepared. It has been prepared by the action of concentrated sulfuric acid on sodium or barium xenate. This is sodium xenate and this is barium xenate. It may be purified by vacuum sublimation at minus 78 degrees Celsius. Now, this XeO64 negative in acidic medium, it gives H4XeO6 and gives XeO4 when water is removed, right? It is unstable and it decomposes to xenon and oxygen. It is very explosive and explodes even at -40 degrees Celsius, right? So it explodes even at such a cool temperature. It has a tetrahedral structure. We'll discuss the structures later. Now, let's see the compounds of other noble gases. Here we have krypton difluoride, right? Preparation: krypton and addition of fluorine in the presence of gamma rays at -193 degrees Celsius gives krypton difluoride. It is a colorless solid, easily hydrolyzed. An addition of water gives krypton, oxygen, and HF. It is a powerful oxidizing agent and fluorinating agent. Oxidizing, fluorinating. It forms adducts with SBF5, ASF5 as the other compounds were doing so. Right? Forms adducts, and you can write it as ionic form also. So there is a question for you. Are the compounds of helium and neon possible? So let's see the answer. In normal state, all the s and p orbitals of xenon, krypton, and radon are fully filled. We know the electronic configuration is ns2 np6. However, there are vacant d orbitals in the valence shell which allow for the promotion of one or more electrons from d orbitals for the formation of unpaired electrons. So the vacant d orbitals may accept electrons. If this be the case, it seems that helium and neon will never form compounds because they do not have d orbitals. The promotion of electrons from s or d orbitals to next shell is highly unfavorable, right? Moreover, the ionization energies of helium and neon are considerably higher than those of xenon and krypton. This fact also rules out that possibility of formation of compounds of helium and neon even with fluorine and oxygen. We'll be doing more such type of questions in one more video, so that if anything is missed in this chapter, you can get that material in the next video. Now comes the structures. The structures, this part is very easy to remember and it is very interesting also. Let's see. The first one is XCF2, xenon difluoride. Just remember the atomic number of xenon. It is 54, right? So the electronic configuration is going to be ns2 np6, as you know. So here it is 5s2 5p6, 5s2 5p6 4d10, right? So we have to draw the 5, n is equal to 5 only. Xenon in ground state is fully filled, 5s2 5p 6 electrons, and d is empty. In the excited state, we have to fit 2 fluorines here, so we need 2 partially filled boxes. So here we excite 1 electron to the d orbital here, this one. So we get 2 empty spaces where we can put fluorines. So it is XCF2. So how to write the hybridization? Just write from S to P full. It is P S1, P1, 2, 3 and D 1 box. So it is SP3D. So now how to see bond pairs and lone pairs, because we have to draw the structures. The number of fluorines decides the bond pairs, right? There are 2 fluorines, so 2 bond pairs, and the rest 1, 2, 3, they are lone pairs. Let's draw the structure. Xenon and fluorine, they form a linear geometry in this way, FXEF, and the lone pairs are on the equatorial position, fluorines are on the axial position. The shape is linear. Shape is decided by the bond pairs only, and geometry is decided by both lone pair and bond pair. So it is a trigonal bipyramidal geometry, and the shape is linear. Next is XCF4. Xenon in ground state is fully filled. we need to fit 4 fluorines, so we need 4 empty boxes. We'll excite 1 and 2 electrons. So 4 places will get empty. Here we write fluorines, 4 fluorines, 4 bond pair. 2 boxes just fully filled, we have 2 lone pair. So the geometry, the hybridization is sp3d2. Alright, the shape is square planar because 4 bonds are there, so we draw it in the plane, square planar, and octahedral geometry because lone pairs also contribute to the geometry. Here we have XeOF2, fully filled xenon. Xenon in ground state, we have to fit 2 fluorines and 1 oxygen. We know 2 fluorines, they need single electron, and oxygen needs 1 sigma bond and 1 pi bond. So it needs 2 vacant spaces. So let's see. Here we can excite 1 and 2 electrons. We get 1, 2, 3, 4 empty spaces. In the first 2 we put fluorines, and in the third one we write oxygen, and the fourth is the pi bond of oxygen because we know that oxygen forms a double bond. So the hybridization is sp3d2, or it must be sp3. Yes, it must be sp3d because one bond is sigma and the other is pi. The contribution to hybridization is only of sigma bonds. So sp3d is the hybridization, not d2, right? So the number of bond pairs are 1, 2, 3 because there are 3 atoms we are adding, and the lone pairs are 1 and 2. So let's draw. It is a T shape, this way, 1 T shape, and because of lone pairs the geometry is trigonal bipyramidal. Oxygen at equatorial place and fluorines at axial positions. Next we have XeF6. 6 fluorines we have to add, so we need 1, 2, 3 excitations. 1, 2, 3, 4, 5, 6 fluorines can be added here now. So sp3d3 hybridization, 6 bond pair, 1 lone pair. Geometry and the shape we have drawn here. It is controversial. It has a controversy. Some says that the shape is this, and some says that the shape is this. Due to sp3d3 hybridization, the molecule should have pentagonal bipyramidal structure, but it is slightly distorted on account of presence of a lone pair of electrons at one position, as we have shown here. However, there has been controversy regarding its structure. It preferably believed to have a distorted octahedral structure, in which all the 6 positions are occupied by fluorine atoms, and the lone pair is present at the center of one of the triangular faces, as you can see here, right? Now let's see the next compound. The next compound is XeOF4. Here we need 4 plus 2, 6 empty places. We need to excite these 3 electrons, 1, 2, 3. 6 empty spaces are there. Now 1, 2, 3, 4 fluorines, 1 oxygen and 1 pi bond is drawn. So we have sp3d2 hybridization, 5 bond pair, 1 lone pair. Oxygen in axial position and 4 fluorines in equatorial and 1 lone pair in the axial. So we have a square pyramidal shape and octahedral geometry. I think by now you have learned how to draw the structure. Next is XeO2F2. We need 1, 2, 3, 4, 5, 6 places. 1, 2, 3 excitations. 1, 2, 2 fluorines, 1, 2 oxygens and 2 pi bonds. These are the pi bonds. Alright. It is 4 bond pairs because we have 4 atoms and 1 lone pair. It is a seesaw shape, as you can see here. Let me show you how it is called a seesaw shape. This is the center and these are the ends. So it looks like a seesaw here. Right? So this lone pair in equatorial position, it forms trigonal bipyramidal geometry. The next compound is XeO3. Don't forget, it is explosive. So xenon, we need to excite again 3 electrons to get 6 places empty. We put 3 oxygens and form 3 more pi bonds here. So the shape is pyramidal. It forms like a pyramid. So it is called a pyramidal shape. And geometry is tetrahedral, as you can see. Next compound is of krypton. It is KrF2, krypton difluoride. The configuration is again NS2 and P6, but you know that E, Ni, or Karina, X-ray, Heme. In this way, you can say this is xenon. We have written N is equal to 5. So for krypton, N will be equal to 4. 3, 2, 1. This is to remember the electronic configuration. N is equal to 5. So 5s2, 5p, 6 for xenon, and for 4 krypton, it will be 4s2, 4p6. So it is fully filled now in the ground state. In the excited state, we have excited 1 electron because we just have to fill 2 fluorines. 2 places are empty. We can write the fluorines. The hybridization is sp3d, 2 bond pair, 3 lone pair. 2 bond pair, so we form a linear shape, and the geometry is trigonal bipyramidal, as you can see here. One very important question is left. Let's do it. What caused delay in the study of chemistry of noble gases? What prompted Bale to prepare the first noble gas compound? In 1962, it was thought that noble gases cannot form compounds because of the following reasons. The atoms of noble gases have completely filled stable electronic configuration, that is NS2 and P6. They have very high ionization energies, and the noble gases have almost 0 electron affinities. Therefore, the noble gas atoms have no tendency to gain, lose, or share electrons with other atoms. As a result, the chemist did not seriously try to prepare compounds of noble gases. In 1962, Neil Ballet, during his study on the properties of platinum hexafluoride, that is PTF6, observed that it combines with molecular oxygen, that is O2, to form ionic compound, that is dioxygenyl hexafluoroplatinate 5 in +5 oxidation state, that is O2 positive, PTF6 negative. Oxygen on reaction with PTF6 forms O2 positive, PTF6 negative. Right? This indicates that PTF6 is very powerful oxidizing agent, and it oxidizes oxygen to O2 positive. Now, oxygen and xenon have some similarities, and this led Bale to try reaction between xenon and PTF6 in a similar manner. So, what is the relation between this reaction and the noble gases? They say that the oxygen O2 is similar to xenon. So we can try xenon in place of oxygen and reacted with PTF6. For example, the ionization energies of xenon and oxygen are close to each other. That is 1170 for xenon, and for O2 it is 1175. So their properties might also be same. On this basis, Bale reacted xenon and platinum hexafluoride in gas phase and obtained an orange-yellow solid. this orange yellow solid of composition XCPTF6. This compound was found to be an ionic compound in the form Xc positive PTF6 negative. In the same way, earlier we got O2 positive PTF6 negative. Here we got Xc positive PTF6 negative, and became the first compound of any noble gas. Xenon plus PTF6 give this orange yellow compound. After this exciting discovery, several other compounds of xenon with oxygen and fluorine in different oxidation states were prepared. So this was the beginning of reactions of noble gases. So this was about the chapter Chemistry of Noble Gases. This video is getting longer, so I think I should make the questions in the next video. So stay tuned. Don't forget to subscribe the channel, like the video, and share it with your friends so that everybody can be helped from this video. Okay then, thanks for watching. Bye bye.